Okay, so let's talk about the sampling distribution. All right, what is a sampling distribution? Now, you're familiar with other kinds of distributions, especially distributions of raw scores, but a sampling distribution is a little bit different. It is a sampling distribution of all the possible means that could be taken from a population of a given sample size. Okay, so it's a hypothetical distribution. We don't actually collect all the possible samples that we could get from a population, but we can create a distribution based on data that we do have. So you can kind of imagine it like this. Here's our target population. We take a sample. Now, how many samples could we take? Well, we could take pretty much an infinite number of samples, and each of those samples will have a mean and their own standard deviation, right? But we don't have the resources to do that, and we're probably not really all that interested in doing that anyways. So we need to estimate what that distribution kind of looks like. So we know, for example, that a sample statistic is not expected to be exactly equal to its corresponding population parameter. So for example, for any sample that we take from a population, we don't expect the mean of the sample to exactly equal the population mean. Now the good news is it's not biased one way or the other. It's not biased toward being higher or lower than the population mean, but we don't expect it to be the same. That should make sense, right? Because if we could take an infinite number of samples, we wouldn't expect every sample mean to be equal to every other sample mean. Now, with regard to the sample variance, that's also the case. We don't expect the sample variance to equal the population variance, and by extension, we don't expect the sample standard deviation to equal the population standard deviation. Now, of course, we have talked about in other videos that the sample variance, it tends to be an underestimate of the population variance, so we have to correct for that. But anyways, the point is that we don't expect samples to exactly equal their corresponding population parametrics. So the difference between the sample statistic and its corresponding population parameter, that's called sampling error. It doesn't mean you did anything wrong in the experiment, just means we don't expect the sample statistic to equal the population parameter. And it's always present whenever we sample from a population, so we need to estimate what that is. Now again, there's an infinite number of samples that we could take from a population, and we could calculate an infinite number of sample means, sample standard deviations, and that implies a new type of theoretical distribution. So you can kind of think of each of these curves here, let's see if I can, there we go, each of these, right, to represent a distribution of scores from a sample, and we could collect an infinite number of samples. And if we did that, then we could actually compute the mean of all these sample means, right? So these distributions, right, we could get an average of all the means, and that creates a new kind of distribution. It's a sampling distribution of essentially the means from all these different samples. Okay, now the cool thing is that the mean of all the sample means is going to equal the population mean. Now why is that? It's because the sample mean is an unbiased estimator of the population mean. So if you take the mean of all those sample means that we could collect, it's going to equal the population mean. So characteristics of the sampling distribution, it's theoretical, right? We don't actually collect tons and tons of samples. We're going to use data from just the sample we collect. And it's not possible to collect all the possible random samples from the population. Therefore, we can't calculate the mean of all the possible random samples that we take. We're going to have to estimate that. And you use information from one sample to infer the properties of the larger population. But again, the sample you're collecting is only one of many possible samples. So we're going to have to estimate the amount of sampling error involved in this estimation. And how much error is there? Well, that's a really good question. Okay, so we're going to need a way to calculate that. And the cool thing is we actually have a theorem that tells us how to do that. That's the central limit theorem. And what the central limit theorem is going to do is it's going to tell us how to calculate what's called the standard error of the mean. In other words, the standard deviation of the sampling distribution. So we're going to be able to do that mathematically, and that's coming up next. So here's the big picture. The sampling distribution of the mean, or more simply, you'll hear it called the sampling distribution, is a theoretical distribution. And it's really all that refers to is the difference between a sampling statistic or a sample statistic and a population parameter. And because you could create an infinite number of samples, what ends up happening is the sampling distribution of the mean is a distribution of sampling error. Okay? And we never collect all the possible samples from the population, so the sampling distribution is inferred based on data collected from just one sample. So it may sound a little complex right now, but and it's probably one of the hardest concepts for students to understand in statistics, is this idea that everything we do later in statistics is going to be based on this theoretical distribution that assumes normality, right? Bell-shaped curve. And that we actually calculate something called the standard error of the mean, that all that is the standard deviation of this theoretical sampling distribution. Okay, so next we're going to talk about central limit theorem, and I hope to see you there.